Greetings, everybody. It's 11:15 now, so we're going to go ahead and get started. My name is Elijah Ellison, and I serve on the Student Executive Board for the School of Data Science. I would like to welcome you all to the 6th Annual Charlotte Women in Data Science Virtual Conference, hosted and sponsored by UNC Charlotte's School of Data Science and Lowe's Incorporated. The Women in Data Science Conference initiative aims to inspire and educate data scientists across the region, regardless of gender, and to support women in the field. With the current state of the world mainly interacting online, we are very grateful for your decision to attend our two-day virtual event and to show your support for our various speakers. I'd like to extend a special thanks to all of our attendees for showing up and showing your support. I'm happy to introduce our speakers for the hours. We have Dr. Jay Chen, who is Managing Director in Corporate Model Risk at Wells Fargo, and Dr. Vivian Zhao, who is a quantitative analytics specialist, also from Wells Fargo. Now our speakers will present, and we will have a brief Q&A at the end of the presentation. If you have any questions, you can go ahead and write them in the chat box, or save a question to the end, and we should be able to turn your mic on and you can ask as well. Thank you so much.
Thank you. So I'll start presentation. I'm Jay, and we also have Vivian here. So today we are going to present unwrapping the black box of the machine learning and the applications in banking. So artificial intelligence and the machine learning has been rapidly adopted over different financial institutions to improve business decisions, customer experiences, and the risk management. So AI and machine learning have been used in the traditional applications where statistical modelings are used, and they are used to improve performance and speed. They can also be used for benchmarking and comparing the traditional statistical modeling. Examples include credit decision, fraud detection, and so on. And right now, AI and machine learning have also been used in areas where traditional statistical models are not used typically. For example, the natural language processing. And for natural language processing, and the common examples include chatbots, complaint analysis, customer assistance, and so on. So AI and machine learning, they are identified as models according to the bank's regulation SR 11.7 because they perform quantitative estimation and the output contains uncertainty. So AI and machine learning has a wide range of applications in different lines of business in the bank. So including credit risk modeling, capital market modeling, financial crime modeling, and NLP modeling. For credit risk modeling, supervised machine learning, for example, random forest, gradient boosting, neural network have been used for both credit scoring models and the stress testing models. And for capital market, AI and machine learning have been used for both derivative pricing and the value-added risk VAR. For derivative pricing, both reinforcement learning and the backward stochastic differential equation neural network can be used. And for VAR evaluation, generative adversarial network, also called GAN, can be used for the time series simulation. For the financial crime model, including both the fraud detection and the anti-money laundering, and all of the supervised learning, semi-supervised learning, and unsupervised learning can be used. For the current emerging area, NLP modeling, for example, complaint topic model or chat intent classification, usually the deep learning are used. But sometimes traditional supervised learning can also be used. So machine learning and AI are identified as models. So they have embedded or intrinsic the model risk. And compared to the traditional statistical modeling, and AI and machine learning has some specific or it's kind of a model risk we need to focus on. First, we need to understand and manage data bias and limitation, because almost all the machine learning and AI models, they are data-driven. So the data bias will also cause the modeling result bias. And the second, we need to build a sound modeling framework and make the machine learning models trustworthy. So for this point, we need to make the machine learning models transparent, understand input-output relationship, and so on. And for this presentation, we're going to emphasize on this point. And the third point is the model replicability and stability. And we know that for machine learning, complicated machine learning and AI models, usually it has overfitting issues, and also they have like a random initialization, random seed. So all of this may impact the model replicability and the stability. So we need to test more. And then we need to conduct ongoing performance monitoring and manage model changes due to model retraining, especially there's a data shift in different periods or different areas. And lastly, we also need to have better implementation control, especially when the models are gone wrong, and we should know how to detect and manage the situation. So for this presentation, we are going to focus on how to make the machine learning transparent. So it's important to open the black box of the machine learning. We know that for supervised learning algorithm, for this presentation, we'll focus on the supervised machine learning. And usually they have very good predictive performance, but the big concern is its black box nature. It's very difficult to interpret. And this is almost true for all the ensemble machine learning algorithms and the support vector machine and the neural network deep learning. Some other algorithms may be more transparent, like Lasso. And it's very important to interpret and explain the results of the machine learning algorithms. And this is to satisfy the regulatory requirement and to help manage model risk and get insights from model and the business perspective. And when we look at or inside the machine learning algorithm, we try to answer questions. For example, what variables are important? What are the most important input and output relationships? And how the correlation impact the response surface? And is the relationship indicated from machine learning is consistent with the business findings? So machine learning actually right now is a very hot area, active area in the research. So there are different types of the interpretation tools or the methods here. So we give a very quick review. So first one we called post hoc explainability. For this one, the modeler will build or run the black box model first, and then we can apply explainability tools to the fitted results. And tools include LIME, SHARP, PDP, ALE, and so on. And for the second category is called the model distillation. For this one, we also first run the black box model. And then we use simplified surrogate model to explain the complicated machine learning models. For example, surrogate global tree or surrogate like a local linear model and so on. And then lastly, we want to introduce the category called the self-explanatory model or self-interpretable model. And for this type of the models, rather than building a black box model, we would like to build inherently interpreted models. And actually today we are going to present two interpreted models. So first one is adaptive explainable neural network, also is short for AXN. And the second one, Vivian is going to present the CNN text classification. Okay, so right now I'm going to talk about the first interpretable model called adaptive explainable neural networks, AXN. So first, we're going to talk about two blocks of the AXN. First is explainable neural network, XNN, and second is GAMNet. And for the explainable neural network, we first will talk about additive index model. This is a kind of statistical model, additive index model, as you can see the form here. It's a very general form. First, you have a linear combination of the predictors, for example, the beta 1x. And we call this projection. You have multiple projections, like a beta 1x, beta 2x. And then for each projection, we apply nonlinear transformation G1, G2, Gk. We call this ridge function. So this additive index model actually is a very general model form, because if the projection is a univariate form, and then this aim, the additive index model, will be converted to the generalized additive model. So in another way, the generalized additive model is just a special form of the additive index model. But however, sometimes the from statistical modeling perspective, is not easy to fit. So we are considering to use a neural network to help the fitting and improving speed. So we build a structured neural network, which is designed to learn this additive index model. And the network structure is chosen to match the structure of the A model. So as you see in the middle is the explainable neural network architecture. First, we have the projection node. The circle one means the projection node. And if you are familiar with the neural network, you know that we have a linear combination of the variables, and we apply the activation, the functions. So for the projection nodes, we apply the linear activation functions. And then we have the subnetwork, as you see in the box here. So the subnet has univariate input and univariate output. And inside the subnet is fully connected, multi-layer, and use nonlinear activation functions. And so as you see, each subnet actually is to learn the ridge function G1, G2, Gk. So this is a kind of the basic, the architecture of explainable neural network, XNN. Let's see, the next block is called the GAMNet, Generalized Additive Model Net. So for this one, as we mentioned, it's a special form of the additive index model, and inside the ridge function, it's a univariate case. So for the neural network architecture, it's simpler. We do not have the projection layer, the beta x. So each predictor will be directly connected to a subnet, and then has output. Okay, so after introduce these two blocks, and then we are going to introduce our framework, the additive explainable neural network. So this new algorithm aims at achieving two goals, both the good predictive performance and also the model interpretability. For achieving this, the good performance, we build an ensemble of a series of GAMNets and a series of XAN, and using a two-stage process. And this can be done through both boosting and stacking ensemble. For interpretability, we perform the ridge function decomposition. So we can decompose the prediction into main effects and interaction effects. Compared to partial dependence plot, PDP, there's no extrapolation concern for our method. And also, both the main effects and the interaction effects can be visualized when we have the lower dimension. And on the other hand, we can also look at importance of the main effect and interaction effects. From computation and tuning perspective, we leverage Google open source AdaNet, and we can use distributed computing to improve the computation efficiency. And we can also leverage the strengths of AdaNet in the automatic neural network architecture search. So then the whole training requires less tuning. Okay, So then I'm going to introduce the flow chart of the AXN. As you see here, we have two stages. The first stage is we build an ensemble of base learners of the GAMnets. So the first box represents the first stage, and there are a couple of iterations. Each iteration, we use a base learner from the GAMnet, and then we assemble them together. And then for the second stage, we do the similar thing. However, we build another type of the base learner through the AXN explainable neural network, incremental to the first stage. Why we do that? When we use the GAMnet, it's used to capture the main effects, as you see from model form there. And then when we incrementally build the base learner through the XAN, the explainable neural network, then we capture the interaction effects. And as you see, there are a lot of iterations. So we pull the iterations together through the ensembling. There are two ways of ensembling. The first one is boosting. The second one is stacking. For boosting, probably everyone is familiar with gradient boosting. So generally, it's a kind of you fit a residual of the fitting from the last iteration, and then do the iteration again and again. And for the boosting, the goal is to reduce the bias through the iteration. Average. A representative is like random forest. The goal is kind of you assemble the strong learners and reduce the variance. So boosting and stacking have very different mechanisms. The first one is to reduce the bias, and by combining the weak learners. The second is to combining the strong learners to reduce the model variance. Okay, we talk about the algorithm, then we move to the interpretability. So we do the ridge function decomposition by grouping the ridge functions with same projection coefficient patterns. So finally, the phase response F hat can be decomposed into the main effects and the interaction effects. If you look at the formulation in the middle of the slides, you can see first we know it's a two-stage process. The first sum represents the first stage ensemble, and the HI is the base learner from the GAMnets. And this is to capture the main effects. And then for the second stage, we have a weighted ensemble of the XN base learners. And then this part is used to capture the interaction effects. And we can rearrange those projections according to the projection coefficient patterns, and we can read them into the main effects in terms of the different variables, and also interaction effects among different combinations. And we can visualize these effects and also calculate the importance of the main effects and the interaction effects by standardizing their variance over the overall data variance. Okay, so we're going to provide two examples to demonstrate our algorithm results. The first one is a simple synthetic example. For this example, you can see it's a regression, and we have main effects of the linear term, quadratic, cubic, and exponential terms. And then we also have two second order terms. And similar to other model, we partition the data into training, validation, and testing data sets. And the testing MSE is close to 0.01, which is very similar to the noise level. So the R square is very high, indicating very good fitting. And we can look at the convergence path. That is the loss function, the MSE, over the iterations here. So you can see a kind of the deep decrease here after the first stage. So further, we show the more information over the iterations. As you can see, for the first iteration, we use the GAMnet, the base learners. And then for the remaining 10 iterations, since GAMnet cannot boost performance anymore, so the algorithm will automatically choose the XAN instead to capture the interaction effects. And for this example, we use a single layer for all the base learners. And then the GAMNet can help us to automatically choose a number of the units for each iteration. So from the interpretability, as you can see, we can plot both the importance of mean and interaction effects, and also we can look at input and output relationship directly. On the left-hand side of the slides is the importance of mean and interaction effects. The bottom one is the true importance, and you can see the ranking is X4 is the most important, and then you have X1 and X3, and then we have the two pairs of the second order interactions. And then at the top, we show the importance from AX and N, and you can see it has exactly the same order and similar magnitude compared to true importance. On the right-hand side, we visualize input and output relationships. First, we look at the main effects from the first stage, and it correctly captures the linear, quadratic, cubic, and exponential trends. And also the interaction contour plots are shown at the bottom on the right-hand side. It also shows a correct pattern. Then we move to a little bit more complicated real example. So this is a randomly select subset of 1 million observation for a residential mortgage example. There are 14 predictors, and here are some important ones like FICO, LTV, delinquency at snapshot dates, unemployment rate, balance, the prediction horizon, or some indicator over time. The goal is to predict the probability of default over the next 9 quarters based on both loan characteristic variables and macroeconomic variables. I didn't have time to post the performance here. So for the prediction performance, actually it's a little bit worse than the XGBoost. We compared the prediction to the XGBoost, random forest, and the multi-layer fully connected neural network. And we use both the boosting and the stacking method for our AXN. So among all of them, XGBoost performs the best, but our result is comparable, and our result is better than the random forest and the multi-layer fully connected neural network. So here we'll more emphasize on the interpretability. So first we look at the variable importance. So for the variable importance, as you see, right, this is a kind of the importance, the plots, and on the left-hand side, it shows the variable names and which stage we obtain this effect. So usually for the GAM, it's the main effect. It's only one variable shows here. And for XN, we capture interaction effects. So usually more than one variables will be shown. So as you can see from the importance from both boosting and the stacking, and they have consistent ordering of the main effects. For example, LTV forecast, and then FICO, delinquency at snapshot, the pre-modification indicator, and so on. And on the other side, let's look at the interactions. They also have the similar patterns. And the first, the top important ones are FICO and LTV forecast, and also delinquency status and horizon, and also FICO and settle. Okay, so after we know the importance, we also want to explore the relationship, input-output relationship. So we plot the main effects of the top 3 variables, LTV forecast, FICO, and the delinquency. And you can see LTV forecast has an increasing trend for the probability of default. The higher loan-to-value ratio, the higher risk to default. And for FICO, and we have decreasing trend, the high FICO means lower risk to default. So it means that lower probability. And for the delinquency, the one represents the current population. So definitely it has a lower risk to default. So it's consistent with people's intuition. And let's look at the interaction effects. We look at the top one, the FICO LTV forecast. And the loans with high FICO are more sensitive to the change to the loan to value ratio. So if you look at this the FICO, right? So you have the pure interaction turns from the negative to the positive. So if you add on to this LTV forecast, it means that it has steeper slope. It means that more sensitivity. If we look at delinquency in the horizon, we just look at the red line here, right? Red line here represent the delinquent population, red line represents the current population. So as you can see, the probability of default goes up because when the time passes by and there's a deterioration of the quality of the current loans, and the current loans will go delinquent over the time. Okay, so I think I finished my presentation. So, and then Vivian is going to introduce the convolutional neural network text classification. Vivian?
So I will introduce the basic steps that we use in the text classification model and how we unwrap the black box of the text classification so that we can easily to interpret the model. Okay, so first I will introduce the structure of the text classification model and then how we can extract the text features from the max pool layer, and then how we can open the box of the feed-forward neural network after the convolutional layer, so that we can interpret the feed-forward neural network, and then we will finally provide the region-wise local explanation to the text data. So throughout my presentation, I will use the Yelp review data to show the results. So the Yelp review is a binary classification problem, so that the reviews will be classified as positive or negative review. Can you go to the next, please?
Okay.
Yeah, so here is the structure of the syntax classification model. So as you can see, this can be decomposed into two parts. The first part is the feature engineering part, and the second part is the classification part, which we call it ReLU-DNN or feed-forward neural network. So the feature engineering part consists of the input embedding layer. So if you are, so maybe not everyone is familiar with NLP models. So in NLP, usually the words or tokens will be mapped into high dimensional vectors. For example, here, every word or tokens are mapped into a 5-dimension vector. And the sentences will finally be mapped into a matrix of the length. So the dimension of the matrix will be the length of the document times the embedding dimension. So the input layer will be fed into the convolutional layer where the convolutional functions will output a vector, and each vector will be put into the max pool, which is taking the maximum value of the vector. So such kind of convolution function will be used for example, here we show 6 different convolution functions in different sizes. So in practical, usually we'll use 50 or even 100 different convolution functions to extract different meaning or information from the original input of the text document. So as we know that each convolution function will finally output one specific value after the max pooling. So here, for example, the red one, it's finally output to one value, real value of the red box here. if we have 100 different convolution functions, and finally we can connect them together, we will have a vector of 100 outputs. So these outputs, we call it extracted features from the text inputs, will be inputted into the feed-forward neural network later, which is the white boxes shown here. And this feed-forward neural network is then doing the classification modeling of the text input. And finally, the final output will be the probability of each classes that the text belongs to. Okay, so from here we know that. Oh, sorry. Okay, go back. Yeah. From here we know that the entire model consists of two parts, and we will train the entire model together. And model complexity, which is very important in the interpretation of the model, is decomposed into two parts also. That is the complexity of the feature engineering part and the complexity of the classification part. So the first, the feature engineering part complexity is usually represented by the number of convolutional filters that we have in the convolutional layer, and we represent the complexity of the classification part as the number of hidden neurons and in the hidden layer of the feed-forward neural network. So the importance of the interpretation of the Bayesian text classification model is that usually a more complex model will give us better prediction performance. However, more simple model will give us simple, easier interpretation of the original model. We will show later how we will be creating as simple as possible model, but with comparable performance to the complex structure. Yeah. Next, please. Okay. So first, we compare the performances of the different settings of the convolutional feature extraction layer and the complexity of the hidden neuron feed-forward neural network layer. So here, by seeing the accuracies on the different settings that we have from 3 to 50 number of features. And also we plot different lines represent different number of hidden neurons in the classification layer. We can see that as we increase the number of features, the accuracies are increasing significantly. But we cannot see a consistent increase or differences in the performance of the accuracy that under different number of neurons, which means here we can conclude that the number of features, which is the complexity of the feature engineering layer, is much more important than the number of neurons, which is the complexity of the classifier layer. So this will make us lead us to think about the model structure that we can use as more as number of users possible, but without using too much number of neurons, so that the classification layer will be much simple. Okay, next, please. So another way of simplifying the model is putting the L1 regularization in the classifier layer. So the reason is that the classifier layer, so we will see the influence of L1 regularization on the complexity of the classification layer. So as we add the value of lambda for the L1 regularization, you can see that the text data accuracy fluctuates at the very beginning, but we can see a significant drop as we increase the lambda. And from the right plot, we can see that even we add a little bit penalty on the loss function, we can see a significant drop of number of local linear models, which means a significant drop in the model complexity of the feed-forward layer. This leads us to think about like adding a small penalty to the feed-forward neural network and still getting a similar performance from the original unpenalized model. Okay, next, please. So after we train, after these experiments, we finally choose to use 50 number of filters per size for 3 different sizes of the filter. Oh, and then we choose to use 1 hidden layer with 10 hidden neurons and apply L1 regularization with lambda equal to this value. And by looking at this structure and training the structure of the CNN model, we finally get 70 local linear models or regions in total for all the out of sample data. And here is a plot of the regions and the number of samples in each region. And this number of samples are in log-10 scale. And most of the regions contain less than 10 samples. And there are 3 regions that have more than 1,000 samples. And these regions contain most of the sample of all the out of sample data. Next, please. We also plot the positive percentage in top regions. So here, in region 1, we can see that the prediction score are mostly near 1, which means this region contains mostly the positive samples, and region 2 is then negative. So the top region is actually biased, which means we can see from the results that the feed-forward neural network, which is the classification layer, tends to divide our text samples into different regions that contain nearly positive or nearly negative samples. Next, please. Here is a plot of the 70 different regions corresponding to 70 linear models in our text classification model trained finally. So we know that linear models is easy to explain, right? The beta of the linear model corresponds to the influences of the specific values on the model. So here we have, because we have 50 different convolution functions per size, which means in total 150 different filters. This will extract 50 information per size, and in total 150 information from the original text data. So these 150 values will be put into the classification layer, and because we decompose the classification layer into 70 different linear models, And by looking at each of the linear models, we can know that each of the extractive features has different influence on the final output of the classification model. So several of them have positive influence, and some of them have negative influence. So later on, we will show that what does each feature extractive filters mean in our CN text classification model. So next, please. Yeah. So we look at the region 0, region 1 only. So remember that we have 70 regions in our C4 neural network. So each region is corresponding to one specific linear model. And we have 150 filters. And here I show the top 8 filters. The top 8 means the beta, the weight of the linear model in this region is the highest positive value. So it's ordered by the highest to the lowest. And I only pick the top 8. And the rows represent different text input. So we have more than 10,000 text inputs, and I only show the top 8 text input here. So in region 1, we have 3,000 samples. So the text samples are ordered in the direction of prediction score. So the top prediction score is the one that the model predicts that its highest probability of being classified into a positive review. And then the top 8 are all extremely positive reviews, and the top columns are the top filters that receive the highest data in the linear model. So by looking at each filter column-wise, so for example, the filter 149, we can see that it's actually corresponding to the original text trigrams. By trigrams, I mean the 3 words or 3 tokens connected together. So they are pretty much in a similar structure or similar meanings that are expressing a positive attitude towards the restaurant in Alp. For example, the awesome place to, amazing smell, a perfect amount of, so by looking at these trigrams, we have a sense, or we are able to know what the exact meaning that the filter 149 tends to extract from the original text model, original text input. Next, please. So, yeah, region 2 is an example of negative region that most of them are expressing a negative attitude towards the restaurant itself. So it's ordered in the opposite way, that the filters are ordered by their negative weights. And the samples is ordered with the prediction from the lowest prediction score to the highest. And I also select the top 8 weights and the top 8 samples. So by looking at this region, we can see that the filter 75 received the highest negative weights, but corresponding to some negative attitude. Yeah. Yeah, I think there are additional 2 slides that I also show similar results from the region-wise interpretation, region 3 and region 4. So it's in a similar way that show the results. But I think that's all for my presentation today. This is how we do the interpretation, region-wide interpretation of the CN text classification model. And I think our still we already passed the time, and we need to leave some time for people to ask questions. So yeah, that's all today. Thanks.
Thank you, Vivian. And sorry, we run over the time due to a couple of the technical difficulties. Since this is online meeting, we still have a couple minutes here. So if people have any questions, we can answer them, or we can either answer in the Q&A session, or people can raise it and we can answer. I don't know if there's this will be used for another meeting sessions. So if there's we don't have time, we can just I'm going to answer Q&A in the text box.
Yeah, I think I saw someone asking a question about a sentence embedding technique like Elmo. Yeah, so specific to my presentation today, the CN model doesn't do any sentence embedding like Elmo, but I think this will also be doable, that if we do sentence embedding and then we decompose the Elmo structure into feature like decoding, encoding, and also like feature engineering and also the classification parts. We're able to do similar kind of interpretation. The structure of CNN is special, like in our interpretation, because we need to the task is to interpret the classification model. So the CNN structure is quite clear that it's specific to n-grams, where people will more focus on, and it's easier to like explain to regulators that certain n-grams or certain words are really important when we do the classification of the model. So if we do sentence embedding, then we might not be able to focus on certain words or certain n-grams. Yeah, so that might be a problem.
Okay. Okay, since there's another question, right? Let me just pick up a top one here. So probably I answer the first one, and now I'll try to answer probably in the text box. Why linear regression is commonly used in machine learning model? So linear regression is kind of the classical the models, statistical models is used a lot. I think the most important thing is quite easy and interpretable compared to some other complex machine learning models. So that's the key. We try to introduce like interpretive models here. But if you just use a linear model, it's not sufficient because it lacks, it's not like flexible to represent the data. For example, it cannot capture nonlinearity unless you do the nonlinear transformation. It cannot capture the interactions unless you explicitly put the interaction terms there. So, and also sometimes there's an overfitting issue if you have a lot of correlated variables, and it cannot do the variable selection automatically unless you do something like a lasso or ridge regression. But this is a, in bank, we do have a lot of logistic regression or linear model. Yeah. So we probably have to end the meeting. I'm sorry for the technical discussion, the difficulties, and I'll try to answer the questions after session. Thank you, everyone. Yeah.
Thank you. Thank you, everyone. Thank you, Jay.
Thank you.